The basic principles of star formation are some of the best understood in astronomy. As was discussed in a previous video, if the force of gravity inwards is greater than the force outwards from the internal pressure of a giant molecular cloud, it will start to collapse. That collapsing cloud will fragment as it collapses, forming an entire cluster of stars with a distribution looking something like this. We see this distribution pretty much anywhere in the galaxy that this process happens to occur. But this doesn't happen everywhere. There is a cluster at the centre of our galaxy that bucks the trend. And it bucking the trend puzzled astronomers for a while. Why is it different to stars we see elsewhere? This cluster revealed the reason it is so different, because it revealed the existence of a supermassive black hole at the centre of our galaxy, a Nobel Prize winning discovery for astrophysicists Andrea Ghez and Reinhard Genzel. This supermassive black hole is known to astronomers as Sagittarius A star. Before we get any further into the video, hello, my name is Thomas Rintoul. If you're new, welcome, and if not, welcome back to my channel where we dive into topics in physics and particularly astronomy. Please consider subscribing and let's get back to that cluster. While this cluster, known as the S stars, has been really useful to the astronomy community, there is this lingering question: why does it buck the trend of typical star formation? The reason that it bucks the trend is tied to that really amazing discovery that it was so useful for. That supermassive black hole. That raises another question. What makes the space around a supermassive black hole so special? What makes it different from normal space? That something is gravity. Around a supermassive black hole, the curvature of space-time due to gravity that we see as a force is so much stronger than it is in a more isolated region of the galaxy. This stronger force of gravity pulls on everything in the area. That includes a cloud of molecular gas falling in towards the central supermassive black hole. We know that molecular clouds in normal space only have pressure to oppose the collapsing force of the cloud's own gravity. By adding an external gravitational force from the black hole, we now have a force pulling on the gas in the cloud, opposing its collapse. The difference in force between the side of the cloud closest to the black hole and the side furthest from it being enough to tear the cloud apart. We call this difference in force, this force gradient over an object, in this case a molecular cloud, a tidal force. So if our tidal forces are tearing apart our molecular cloud, then that means no stars, right? Well, no, we can see them. Obviously there are stars. We established in the last video that they couldn't have formed somewhere else and moved inwards. They would have run out of hydrogen fuel to fuse into helium before making it to their current position. They have to be forming from gas around that supermassive black hole. There has to have been a gas cloud around that supermassive black hole that formed these stars, but it will have done it in a slightly different way from normal. As it falls inward and gets ripped apart by the supermassive black hole, it spreads out into a large disk around the black hole. Simulations have shown this to be the most likely scenario for a molecular cloud falling inwards towards a supermassive black hole. The disruption of that cloud allows stars to form in the configuration we see them today, in an elliptical oval-shaped orbit rather than a circular orbit like we see in the solar system. Unfortunately, we're not yet ready to form stars. Our tidal forces aren't quite finished with our gas cloud yet. We know that these tidal forces act to pull our cloud apart, but unlike the cloud's own gravity and its internal pressure, this force doesn't act with the same spherical symmetry of those forces. The black hole's gravity has a preferred direction, radially inwards towards the black hole. The preference for this direction is what is responsible for flattening out the cloud into a disk. When it does this, the cloud is compressed perpendicular to the direction of the gravitational force. Its gas gets squeezed into a smaller volume of space. According to the simple gas laws, that means it must heat up. In fact, simulations by Bonnell and Rice have shown that the gas in this former gas cloud, now a disk, can get to several hundreds, if not several thousands of Kelvin in temperature. This is very hot, especially when we compare the temperature of this gas cloud before it fell in and was disrupted, which was only around 10 Kelvin, very close to absolute zero. So now we have an overly hot disk around our supermassive black hole. How do we form stars? We form stars through a process called fragmentation, specifically disk fragmentation. When enough of the disk mass gets in one area, it breaks apart from the disk and starts to collapse under its own gravity. From there it breaks apart into smaller clumps, smaller cores, and from there forms stars. This is the same process that we see in normal space for normal star formation. So we should be expecting that typical initial mass function, that distribution of stars we see everywhere, right? Once again, no. While the process is very similar to that we see in the rest of the galaxy, we have to account for the heat. This gas is very hot. This is where we return to the Jeans mass, something we discussed in the last video. As a quick reminder, the Jeans mass is the minimum mass of gas you need to be able to collapse down to form stars, dependent on the temperature and the density of the gas. When we account for all the heat in our disk fragment, we find that the Jeans mass is much, much higher than normal. At the low end, it can be as much as 1 solar mass, about twice as high as normal, and at the high end, it can be as much as 50 solar masses, 100 times the typical value. What this does is all but eliminate the possibility of forming the low mass K and M stars that are so common in the rest of the galaxy. Instead, we find a top-heavy initial mass function, full of O, B, and A stars. Our model's predicting exactly what we observe around the Sagittarius A star supermassive black hole at the centre of the galaxy, showing us that these stars likely did indeed form in situ around the black hole, even if it was a slightly more violent process than normal. Thank you for watching this video all the way to the end. If you enjoyed it, then please do hit like and maybe comment down below with any suggestions, questions, or just comments. We've seen some amazing growth on the channel in the last few months, and it would be amazing to make a video answering your questions about astronomy or anything else you'd like to ask. Please drop them down below and on any other videos that come out in the next few months. If you're looking for something else to watch, then why don't you check out this video here. YouTube's picked it out and they think it'll be a pretty good fit for you. If you've seen it already, then why don't you check out my Twitch streams, which are a little more casual, a little more informal, with a bit of science and a bit of video games. I'll see you in the next one. See ya.